Hi, welcome back to Land Use, our discussion of engineering, geology. Essentially, these are common problems, geologic hazards such as floods, earthquakes, and an example, which we'll talk about briefly, which is really a combination of problems, which is the Alaska pipeline. This is a relative cost, annual cost for different hazards, different things that we'd have to do in terms of engineering geology. Um, might be building dams, shoring up dams, retrofitting, um, trying to slow down or stop landslides, building structures for coastal erosion, um, dealing with expansive soil, and then other sort of smaller issues associated with the geology. And we've talked about all of these things to some degree. One of the things to note here is that soil expansion, right? This is essentially the process of creep, that process of mass wasting, is the most expensive on an annual basis. We don't know if anyone was killed. That's what these unknowns here are for. If any lives were lost because of this, maybe your building fell down, some indirect mechanism, but it's certainly on an annual relative value here is much higher than anything else that's out there. Coming up close, but only by half here, we've got floods and landslides, which are fairly active processes, especially if you live in a prone place like California, you're going to get some landslide activity probably every year. Coastal erosion. Coastal erosion tends to be relatively slow, so costly, but not a rapid process like landslides. Earthquakes, one of the least costly things on an annual basis, simply because they're infrequent. Okay, and then flooding tends to be fairly expensive because it's pretty common. Things that we expect to become worse over the course of the years with global warming. Okay, flooding, earthquakes, not so much. Landslides, yes. Coastal erosion, yes. And expansive soil, quite possible. Okay. Flood mapping is done by FEMA, and these are examples of flood maps you could look up on the internet if you wanted to do that. And maybe at some point in this class I will change this around so we do it, an example of it. But everything shown in blue, this is for the Grays Lake region, the College of Lake County, which I also teach at now. The college is down here, so in this map, the College of Lake County is right there. There's a big pond right here next to the college, just like Oakton has, and you'll notice that it's part of the area that will be inundated, which is known as Zone A in that 50-year or 100-year flood period. Okay? There's a description on the right-hand side of all the different features on this map. So what you don't get when you just look at the map online is it doesn't really explain what all the zones are and what all the features are. But when you download that map, you can actually find a legend that explains more clearly what you're looking at. But for our purposes, it's hard to read everything, so we'll just stick with areas sort of in blue here, are regions of flooding on a relatively regular basis. And this is again for the College of Lake County, which had a flooding issue not too long ago, and you can see why. It has a low zone A right to the southwest of the main campus. Okay. Earthquakes, faults. Let's take a look at the seismic activity. In 2008, there was a 5.2 in Mount Carmel, Illinois. It's down here close to this area where we predict relatively high acceleration. This is peak ground acceleration relative to as a percentage of gravity. And so we see this area being 60%, okay, so pretty high. And what's called the New Madrid Fault Zone that's sort of into Missouri and southern Illinois. Why is this zone here? Why are there so many faults here? We think there's some sort of subsurface structure that's down below the bedrock. But you can also see there are lots of faults and folds in this region. And those faults and folds extend up into areas of northern Illinois, okay, and in Indiana as well. Okay. And then up here we would have Des Plaines. We don't see too many faults up there, but there is an interesting impact structure. I haven't talked about it in this class, that's being inferred in the subsurface there, and you can see them dotted around the states in the Midwest. Anyway, this is a hazard map that shows that, well, we don't have too many hazards. Way up here in the northern part of the state, things are not going to be too seismically active. Okay. Coastal erosion, well, we don't have to worry too much about that. A lot of that's managed by the USGS as well. Coastal erosion studies have been going on for a long time, but now we're also interested in sea level rise, okay, and the effects of climate change and how sea level may inundate or advance erosion. Okay. The Alaska Pipeline is an example of an engineering geology. It has to deal with a number of things, not only coming over the serious mountain ranges, the Brooks Ranges, all the way across from northern part of Alaska to the southern part of Alaska. Things that are issues: seismic activity, regulation of oil temperature. The oil needs to be able to flow in an environment that's very cold. We have to regulate the ground temperature, and then we have natural solifluction as a process as well. Notice the oil pipeline here is up above ground, and it's on these sort of stanchions. We have these fins on both sides, and you can see them all the way down. And I'll talk a little bit about these right now. Basically what happens is the oil needs to be kept at a temperature of about 60 degrees, but underground, if the pipeline was underground, this is going to thaw out, okay, thaw out the permafrost in some of these regions. So they put it above ground. The problem is that hot oil or warm oil flowing through here actually melts or radiates heat or conducts heat back into these stanchion poles, which go down into the ground and hold up the pipeline, which again are sunk down into the permafrost. And so these fins are part of a cooling system, and they keep these poles all along here that are part of the support system cool and keep the ground temperature from getting too hot, because if these things get warm and melt the ground or melt the ice of water in the ground, then we're going to start seeing this thing sag. Okay. This is an example of a series of sliders that the pipeline has been put on top of as it crosses the Denali fault zone, which is right back here. Here is the fault zone right here, and here's the pipeline on the left-hand side coming down through the system like this. There's the pipeline there, okay, coming from Prudhoe Bay all the way down to into Valdez. And so the Denali fault rupture here, we see the pipeline has been put on a bunch of sliders. You can see the track here, which has got to be, based on the length of this car, you might put it at, let's see, that's maybe 8 to 10 meters wide. So you get a lot of throw across the fault, and it will just allow the pipeline to shift or to slide as the earth slides under it. So it's not fixed to the ground strongly in this scenario. It sits on, notice, what we call a Teflon shoe. So Teflon is a kind of organic polymer, synthetic polymer, and it's a somewhat, it's got a low coefficient of friction. So a lot of engineering went into thinking about how to keep this pipeline from basically falling over or rupturing. Another problem that you deal with going across the entire state of Alaska, as this pipeline does, is the process of solifluction. This is what's going to happen to the Earth's surface as temperatures rise in the summer. The permafrost in these regions melts, and it creates a slurry of water and sediments or soils. You can see these sheets or these layers here, right along here, and then you come over here, you can see the edge of that part of what is a sort of a hummocky surface right through here and here. These are all areas that are sliding or moving at some point or have moved in the recent past. And this is another thing, oopsie daisies, that can really disrupt, right, these kinds of stanchions. when you have that kind of process of soil effluxion going on. So all of these are engineering concerns that had to go into thinking about the design of the pipeline. And that wraps up our summary of some of the engineering relation or connections to or concerns and issues associated with land use.